I want to talk about some homework problems from MyLabs Plus. That's what I would have done in class if it were live. So maybe I can find some that might be reasonable candidates and spend a little while talking about them to help you out. This is going to be the last of the presentations about polynomials. In the lab on Wednesday, there will be a polynomial work session where you have a chance to apply some of these techniques and figure out what graphs look like, how the information about crossings and x-intercepts that you can get from synthetic division play into what the graph of the polynomial function looks like. So let's look at a couple to see how some of these ideas might be looked at. There have been a couple homework sessions about polynomials. We talked about real zeros. That's the stuff about the rational roots test and how you can associate factorizations of the polynomial function with zeros of the polynomial. And then talking about complex zeros, allowing the possibility that they're not all real solutions. Let's look at some from 5.5. First of all, the real zeros of a polynomial function. Let's try question 5. So I'm supposed to try to find real zeros and use the real zeros to factor f. And to find real zeros, they don't give me any clues that I could look at. So I'm going to have to see what luck I have to generate them. What I'll notice first of all is the possible rational roots are, now the way I write it in general is maybe I'll write a fraction, so a top and a bottom, say p over q, where p divides evenly into the constant term of the polynomial, that is 21, and q divides evenly into the leading coefficient, the coefficient of x cubed, that's 1. I like that situation. A leading coefficient of 1 means that there aren't many possibilities for the denominator of that fraction. The only hope is going to be for it to be plus or minus 1. So that means it's all the divisors of 21 plus or minus. So those numbers are plus or minus 1, 3, 7, and 21. Not too bad. Plus or minus 1, plus or minus 3, plus or minus 7, plus or minus 21. There's only 8 things to check, and I can check them fairly quickly with synthetic division. Let's try 1. But try 1 doing synthetic division on 1x cubed plus 3x squared minus 25x plus 21. What comes out is 1 and add, and 4 and add, and 1 and add. And the fact that I get a 0 out, that's enough. That's good news. That says that x minus 1 is a factor, and my original polynomial, f of x, is equal to x minus 1 times, and now the coefficients that show up for the rest of the synthetic division are coefficients for the quotient. That's x squared plus 4x minus 21. And so the cubic that I started with has this factorization, and what's left over, the complementary factor, is a quadratic, and I can look at that, and in fact it factors by inspection. X squared plus 4x minus 21 factors as x plus 7 times x minus 3. You can multiply that out to make sure that's right. FOIL x plus 7 times x minus 3 to get x squared plus 7x minus 3x is plus 4x minus 21. And in fact, that's kind of useful, but I mean, it's nice to realize that, in fact, if I had started with a different possible rational root than 1, I might have succeeded anyway. That those other values that come out, x plus 7, so x is equal to minus 7, and x minus 3, so x is equal to 3, those were already in my list of possible rational roots. So I've got several real zeros that I can write down. The real zeros are x minus 1 equals 0, so x is 1, or x minus 3 is equal to 0, so x is 3, or x plus 7 is equal to 0, so x is minus 7. Those three numbers are the real zeros, so I'll check to make sure that's right. Good. And that's an answer. Let me save this on my notes and clear my ink, because I'd like to make one more point here before I leave this problem. So 1, 3, and minus 7. So they didn't ask me to graph this, but I can say something about what the graph looks like. Notice that it's of degree 3, which is an odd number, and a positive leading term coefficient. That's this 1 times x cubed for a positive leading coefficient. So the graph has this characteristic as an end behavior, a positive leading coefficient, and a big X will give a large value, so it aims towards infinity when x gets big, and towards minus infinity when x is negative. We talked about this as a general feature of a function, talking about end behavior. It looks like when we talk about rational functions, we had in behavior sometimes it looked like asymptotes. The long-term values of the function could go towards 0 or towards some horizontal line that would represent some other non-zero constant. For polynomials, the only possibility is that it shoots off towards plus or minus infinity for large values of x either way. So if this is degree 3, it's odd, so plus and minus infinity, and a polynomial of degree 3 has at most 3 minus 1, that's 2 turning points. So think about how that could happen. The function is 0 when x is 1. The function is 0 when x is 3. The function is 0 when x is minus 7. And it has at most 2 turning points, and it has to have this end behavior. So it can't cross the x-axis anywhere but here and here. Here I have to spin my second turning point and have a shape that looks like that. We could check to make sure that's right, see how close my rough drawing is. If I look at it on a picture, so let's see, x cubed, 3x squared, 25x plus 21. So if I were going to graph that thing, x cubed plus 3 x squared minus 25x plus 21. Make sure I got that right. X cubed plus 3x squared minus 25x plus 21, and graph it. Maybe I can zoom out a little bit. You see a little bit more of it. It goes way high, see? But I do get it. When I zoom out far enough, I see this shape where it comes down, across, cross, and back down one more time. So this general shape that's doing like this is the shape that I captured when I wrote my homework thing. Let me capture that while I'm here and clear my ink and go back. So that's the answer for that one. Let's look at one where maybe we're going to look at a more complicated version. Try number 9. Okay, so here's something else that I can do. I see use the real zeros to factor f. So I should do that, and that's what I was talking about before. So the factors of f look like x minus 1 and x minus 3 and x plus 7. My MATLABS is more forgiving than the graphing utility because it doesn't make me write the star in between for multiplication. That's easy to forget, so we'll put that in and see that that's okay. So back and forth between what the solutions to the equation are and what the factored form looks like. Now let's try another one. Find the real zeros. Let's do a little bit of testmanship on this. I see they give me this answer as a multiple choice, and they give it so that every possibility in this multiple choice has a possible real zero of 1. So it's a good bet that 1 is a real zero. And I could go with that by using that to get some information out. So let me write f of x as 2x to the 4th plus 3x cubed minus 14x squared minus 9x plus 18. Degree 4 equation has 5 coefficients. And I know it has x minus 1 as a factor because 1 shows up on all those answers. So let's just make sure. Bring down the 2 times 1 and add, times 1 and add. That's minus 9 times 1, and that's minus 9 when I multiply by 1 and add, and times 1 minus 18 plus 18 is 0. So sure enough, I ended up with a solution of 0, and now that means that f of x is equal to x minus 1 times 2x cubed plus 5x squared minus 9x minus 18. So let's try breaking down that cubic further yet. So that saves me a little bit of work if I go with its coefficients. So 2, 5, minus 9, minus 18. And now I'm going to try another possible real zero. They give me some to try, so again, this idea of I'll use the information that they give. This list of numbers are going to work. I see 2 possible answers, A and C, both have 2, as a possibility, so I will try 2 as a possibility, and I'll show you in a minute. I don't care if it works or not in as far as figuring out what the answer is going to be. 2 times 2 is 4, and add is 9. 2 times 9 is 18, and add is 9. 2 times 9 is 18, and add and get 0. So 2 is a solution. So 2 is part of that one, and 2 is part of that one. And the part that's left over now is 2x squared plus 9x plus 9. So let me make sure I did all that right. Bring down the 2 and add 2x squared plus 9x plus 9. And now I'm looking for a solution to that thing. Let's see, does it factor? Sometimes I can factor a quadratic a little bit better. How about if I factor the quadratic as 2x times x and 3 times 3 to be 9. So 2x plus 3 times x plus 3, sure enough, factors as 2x squared plus 9x plus 9. And that would say x is 2x plus 3 is 0, says x is minus 3 halves. X plus 3 is 0, says x is minus 3. So minus 3 and minus 3 halves, that makes C the right answer. So I get that by factoring it all the way down, pulling out the real zeros, so there I'll check that answer and see if that's right. Okay. And see what else I have to do. So let me save this. I think I'll need this to, they're going to change what they're asking after that. So, okay. And now I want to write f in factored form. So what's going on? I know that the answer is 1, minus 3, 2, and minus 3 halves. So there's a factor of x minus 1 and a factor of, so I'm going to read that off. I need a factor of x minus 1. I need a factor of x minus a minus 3, so x plus 3. Factor of x minus 2, and a factor of x minus a minus 3 halves, x plus 3 halves. And I bet one of these answers will have all that stuff in it. I need a minus 1, plus 3, minus 2. I said x plus 3 halves. That's because I had, that was a solution, x equals minus 3 halves was the solution to 2x plus 3 is 0. And that makes this the right answer, and I can see that it starts off right, that if I multiply this all out, I end up with x, 2x times x times x times x. That's the 2x to the 4th power. That's the leading term. So I think it should be A, and I'll check that answer. Okay. I don't think I need to do a similar exercise, but you might want to try another one. Now let's go and look at another homework set. Let's try one from the complex numbers and see what kinds of new ideas are illustrated in those homework. So complex zeros in the fundamental theorem of algebra. Try a couple of these out and see what happens. Let's see what number 2 is. Information is given. Coefficients are real numbers. So the fact that the coefficients are real numbers means that the complex solutions occur in conjugate pairs. So there is I. So the conjugate of I is minus I, and the conjugate of the other one, 16 plus I, is 16 minus I. Think about a situation where there's the quadratic formula being applied to a quadratic equation, and the quadratic equation has a negative number underneath the square root. So a negative discriminant. When that happens, then you have plus that square root of a negative number and minus the square root of the negative number in the calculation for the solution to that equation. And that's that plus or minus square root of the negative number. That's where this conjugate comes from. So that there's hiding behind all the algebra is the solution of a quadratic equation with the quadratic formula. The negative discriminant means that you get plus something times I and minus something times I. Two different solutions from the two cases of the quadratic formula. It happens for plus I to be minus I. It happens for 16 plus I to be 16 minus I. So the remaining zeros, the ones that aren't given, besides I, it has to be minus I, and besides 16 plus I, it has to be 16 minus I. Those are the conjugates that you should report. And let's look at another one in this set. Let me get rid of my ink. Find the complex zeros of the polynomial function and write it in factored form. So I'm going to try to factor that. It's a cubic, so I need to get it down to a quadratic, so that reduces it to a problem from the last section, talking about finding possible rational roots. So let's start it as a problem from the last section. So the possible rational roots are, well, now here again, this is a monic polynomial. Its polynomial is as the highest power, the x term, has degree 3, and in this case the coefficient is a +1, so that's useful. So I'm going to write down possible rational roots are just going to come from factors of 10, so plus or minus 1, plus or minus 2, plus or minus 5, or plus or minus 10. I kind of hope I will find one rational root among those, and if so, the quadratic that's left over will be something I can factor to come up with the quadratic roots for the complex numbers that they're asking for. So let's see what luck we have with that. Possible rational roots. So I'm going to try to factor this. So we'll use the old tried and true synthetic division. 1x cubed minus 4x squared plus 9x minus 10. And let's see, if I feel lucky, I'm going to try 5. And if I try 5, what comes out as 1 times 5 is 5, and add, times 5 is 5, and add, times 5 is 70, and add. Well, 5 didn't work. Let me try minus 5. 1 minus 4, 9, minus 10. You know, I tried 5 and it didn't work. I don't have to try 10 because if I use a number bigger than 5 and do this division, then all across the bottom, I'm multiplying by something bigger than 5 and adding to get a bigger answer. If it's positive all across the bottom, doing a bigger number to divide by makes the numbers even bigger positive. There's no way to make that remainder get down to 0. So I get to sort of save that little bit of work. So 1 times minus 5 is minus 5, and add, minus 9, times minus 5 is 45, and add, and it's 54, times minus 5 is minus 500, minus 270, and add is minus 280. Same kind of reasoning. It didn't work for 5, so all positive numbers across the bottom. 10 is going to be an even bigger number at the end. For minus 5, the numbers are alternating, and that alternation, that oscillation gets more pronounced if I use a bigger number than minus 5 to divide by. So I don't even have to try minus 10. So the only hopes are plus or minus 1 and plus or minus 2. Let's see what luck I have. Let's try plus 2, 1, minus 4, 9, minus 10. Try dividing it by 2. 1 times 2, and add, times 2, and add, times 2, and add. Ha! Bingo! End up with 0. So this thing, that means that f of x factors as x minus 2 and x squared minus 2x plus 5. X squared minus 2x plus 5 comes from those coefficients. X minus 2 comes from f of 2 is equal to 0. That's a factor of x minus 2. So now I can write down f of x in factored form. I can get x minus 2 times x squared minus 2x plus 5. That's one version of factored form. They're asking for complex zeros, so they probably want to see all of the complex zeros. So let's solve this equation. The quadratic formula on x squared minus 2x plus 5 equals 0 says x is minus b, that's 2, plus or minus square root of b squared, that's minus 2 squared, that's 4, minus 4 times a is 1, times c is constant term is 5, all over 2a. So 2 plus or minus the square root of 4 minus 20 is minus 16, all over 2. So let's see, 16 is 4 times 4, and the square root of minus 1 is I. 2 plus or minus 4i over 2, that's 1 plus or minus 2i. So I'm going to write f of x as x minus 2. That's the real root that I found by that synthetic division process, times x minus the other roots are 1 plus 2i and 1 minus 2i. So let's write it as 1 plus 2i, x minus 1 plus 2i for one of the roots, and x minus 1 minus 2i for the other root. So roots are 2, 1 plus 2i, 1 minus 2i. There's one factor for each one of those, and that'll be, if it turns out that's not the answer, I'll report the answer as though I didn't factor the quadratic part. But since they ask for, find all the complex zeros, now I'm looking at the complex zeros and see them all. So I think I got that. I think that's the form they would want. Good. I think that's all they asked for here. Let's see. Similar exercise, so we've got all parts showing. That's good. Let's try one more of these, and then we'll call it quits. 6 is did I capture the ink last time? Can't remember if I did or not. Let me do it again to make double sure. Capture that. And let's try number 6. It's a little bit fancier problem. So let's see how that one might go. I can make up a reason for figuring out an answer. 120. Well, one thing I look at, trying to sort of save a little bit of time, I want to try to complex zeros right after in factored form. I'd like to see if it has any real zeros, first of all. And I notice that if I take x equal 1, then all of the, I'm just looking at the coefficients, and the coefficients are, let's see, plus 1 and 12 and 108, that adds up to 121, and minus 4 and 117, that adds up to 121. So I expect, I guess from that a real zero is x equals 1. And it's going to have a factorization of x minus 1. So let me try that. 1 into 1x to the 4th, 12x cubed, minus 4x squared, plus 108x minus 117. So when I do that division, what comes out is 1 times 1 and add is 13, times 1 and add is 9, times 1 is 9 and add is 117, times 1 is 117 and add and get 0. So it does factor down as x minus 1 times x cubed plus 13x squared plus 9x plus 117. Now let's see what might be true. I'd like to find, so it's a cubic, so if I could find a complex zero, I'd like to get it down to a quadratic, so I'd like to find one more possible rational root, and a possible rational root for x cubed plus 13x plus 19x squared plus 117 could be, well, let's see, 117 is 3 times, 3 goes into 11, 3 times 39, So it's 3 times 3 times 13. X cubed plus 13x squared plus 9x plus 117. Let's try that. See if it's divisible by x minus 3. That's one of the possible factors of that. So I'll try 1x cubed, 13x squared, 9x, 117. Try doing it by x plus 3. So division goes 1 times minus 3 and add times minus 3 and add. It's 21 times minus 3 is 21. 3 minus 3 is minus 63 and add 454. Okay, so minus 3 didn't work, and it's all positive, so there's not going to be anything bigger than minus 3 that works. Let's try minus 9. One, 13, 9, 117. 1 times minus 9 and add. Minus 9 times minus 4 is 36 and add. Minus 9 times 45 is too big. It's going to be a negative number that comes out. Wait a minute. Wait a minute. Minus 9 times, I got my sign wrong, didn't I? Minus 9 times 4 is minus 36. 9 minus 36 is something different. Let me get it. Be careful here. Nine plus minus 36 is 27. Still not quite right, is it? 9 times 27 is minus 27. Minus 9 times 27 is 63. 9 times 2 is 18 and 6. It's 24. And it's too big. So it still didn't work. So let's try minus 13. Just looking for one more linear factor. 1, 13, 9, 117. So 1 times minus 13, let's have some hope, is minus 13 and adds up to be 0. Times 9 is 0, adds up to be 9. 9 times 13 is 7. 1, 1, 7. Ha, ha, ha. And get 0 out. So here's a solution. We found one solution, and here's another solution. So we know that f of x factors as, so f of x is x minus 1 times x plus 13. And now the quotient is x squared plus 0x plus 9. So x squared plus 9 is 0. That if they're asking for complex zeros, so I'm going to use x plus 3i times x minus 3i. And the complex zeros are 3i and minus 3i. Couldn't have found it if I hadn't have gone through and checked that out. So let's see. Huh. What did I do wrong? X squared plus 9. I went through, huh. X squared plus 9. I'll clear my ink and think about this again. Done. What am I missing? 3i and minus 3i. Sure, I factored it right. Oh, darn it. Look at that. I really apologize. Complex zeros, and this was my problem. I saw complex zeros as the zeros that were pure, that had an imaginary part in them. So I reported the answer with just those parts. What I had correct was plus 3i and minus 3i. And in factoring it to get there, I got 1, that factor x minus 1, and 13, x plus 13. I should have just listed those. Those are certain, I mean, they're real numbers, and real numbers are a subset of the set of complex numbers, so I should have listed those too. I apologize for being dumb like that. So with that in, the factors that I found were x minus 1 and x plus 13 and x minus 3i and x minus a minus 3i, so x plus 3i. So all 4 factors are there. And I should, oh well. So I should have remembered that it's a 4th degree polynomial of factors into 4 linear factors. In this case, 2 of them involve complex numbers for this complete factoring. So I don't deserve well done, but I deserve done anyway. And I do feel done. So I'll quit for today and learn from my mistake and learn from the process of breaking a polynomial down and getting information out about what the graph could look like.